Hello everyone. Let's look at those three example problems to linearize nonlinear equations, but this is called local linearization. We will be only trying to linearize the nonlinear functions for a local point, for a given point, or we can just also call this as the operating points. So this is a little bit different from the previous examples that I showed to just introduce you linearization. So for this problem, it asks to linearize the nonlinear equation, which is z equal to x times y. So when you write the function, or this z as a function, this is a function depending on x and y. So you have two variable equation. So the Taylor's expansion method, which is used to linearize functions only with one variable, was equal to function's value at that operating point plus function's derivative with respect to x when x is equal to your operating point multiplied by x minus x bar. Again, x bar is your operating point. But here, since we have two variable equation, or your equation depends on two variables or two input, then your function should be written as finding the function's value using those 2 points plus df dx when multiplied by x minus x bar, which is your delta x. Then you have to also include the derivative of the function. So I have to also rewrite these because they are no longer depending on one variable. So xy. Then take the derivative of the function with respect to y. But this is a slope, so please do not just take the derivative, but also plug in those nominal values or operating points, and this time you have to multiply this by y minus y bar. In the previous examples, I just gave you 1 point, but in this example, which is a little bit different, instead of one value for x bar, I'm giving you a region. So what you have to do, you have to just select the midpoint for a given region. That means your x bar should be equal to 6 and y bar should be equal to 11. Now let's apply Taylor's expansion method for our given example problem. Your f of x y, let me rewrite this one more time, f of x y is equal to x times y. So this should be equal to that. I'm going to calculate each term separately and then combine them together. So here you have f of x bar y bar means function's value when x is equal to 6 and y is equal to 11. So 6 times 11 will be equal to 66. Then continue with the derivative. Function's derivative with respect to x when x is equal to 6 and y is equal to 11. So derivative of x times y, when you take the derivative with respect to s, should just give you y, and x is equal to 6, y is equal to 11 is equal to just 11. Then the function's derivative with respect to only y, so we are taking partial derivatives here. X is 6 and y is 11. So when you're taking the derivative only with respect to y, whatever is next to y will be considered as a coefficient. So this will be just equal to x when x is equal to 6 and y is equal to 11. So this should just give you 6. From here, if you plug those numbers in to your general equation, the linearized equation around those two given points should be equal to 66 plus 11 times x minus 6 plus 6 times y minus 11. So from here, your linearized equation will be equal to 11x plus 6y minus, so from here I have negative 66, those two will cancel out each other, minus 66. So this was the first part of the problem. So it was asking you to linearize your equation around those given points or region. So my linearized equation, okay, if x is around 6 and y is around 11. Now the second part of the solution is find the error. So if you're using the linearized equation instead of this nonlinear equation, then find how much error you're making. This time we're going to assume we're going to select two different points, x is equal to 5 and y is equal to 10. So for these new points, so please do not confuse those two. I'm solving for the error with my new points. So in this case, if x is selected to be 5 and y is selected to be again 10. So in the original function, f of xy using 5 and 10 will be 5 times 10, which is 50. And for the linearized equation using x and y, I have 11 times 5 plus 6 times 10 minus 66, which will give you 49. And then the percent error, it should be function's value, original value, minus the linearized equation divided by 50 multiplied by 100. So your percent error is 2. So you will be making 2% error using this linearized equation when x is equal to 5 and y is equal to 10. So next part is what I want to actually highlight or emphasize is, let's say this was a homework and you were allowed to use Matlab. So how can I solve this problem in Matlab? Is there any way I can get a little bit of help? So I'm going to open Matlab. I really like using live script, so I clicked on live script. So let's just open one. And because the first thing to do is I will define my function. Okay, let's define this function x times y. Because I'm using variables, you have to call symbolic toolbox. So I have two variables, x and y. And your original equation is x multiplied by y. And I don't want to print this, so I put here, I included a semicolon. The next thing, let's look at the linearized function. But maybe I should do this first. I will find these values separately and add them together. You can do all at once, but I'm going to just add them together. So I have the nominal values equal to, I want to substitute in f wherever we see x and y. Okay, I will use my operating points 6 and 11. So let's go ahead and calculate or see the result. So the results will show up on the right part. Okay, the nominal value is 66, so let me check mine. So I didn't make any mistakes, so it's really 66 as well. So I don't need to print this anymore. The second part is, now I want to differentiate the function with respect to x. So f with respect to x. So let's just also run this one. So the f of x is equal to y, which was correct. But then I want to find a slope. So I just call this fx nominal. So I want to substitute in f of x. Again, guys, wherever we see x and y, we want to plug in the numeric values 6 and 11. So this is a great way to actually validate your response. So check this, f of x, y. Y with respect to x using those 2 points is also equal to 11. So I didn't make a mistake. Now let's find the derivative with respect to y. And as you can just imagine, what I will do next is I'm going to substitute the values to find the slope at that point. So fy nominal should be equal to, substitution. So I will substitute in my function f, not capital, in my function fy. Similarly, guys, wherever we see x and y, I can actually copy this part instead of just typing. And go ahead and really calculate your equation. I get also 6. I'm ready to include them all at once. So my linearized function is equal to, remember function's value, I named this as f nominal. Then I will add fxn, which is the slope, multiplied by, so this should be multiplied by x minus 6. Then we have fyn multiplied by y minus 11. So let's see. So this should be my linearized equation, and let's confirm or validate with our solution, 11x plus 6y minus 66. So this was really the first part. Okay, what I want to do next is, let's find the error, percent error. So I want to use my original function. So I will call this f new, okay? And in f new, what we want to do is we want to substitute in f, the original function, wherever we see x and y, not 6 and 11. Remember, we selected 2 different points. One is 5, the other one is 10. So let's calculate this number is 50. And I want to do exactly the same thing for using my linear function. Okay. and substitute in our linearized function the new values 5 and 10. And from here, we will be able to find the percent error. Let me calculate. And then the error should be equal to f new minus f linearized new divided by the true value multiplied by 100. So I'm able to find my percent error here. So this is a way to, if you don't have to show your calculations, if you are trying to linearize the function, or yes, let's say you want to test or validate your response, so you can actually confirm it with Matlab here. I like using it. The second example, so we have another function. This time you're just given a nominal point, and the question is only for linearizing the function about that point. Let me bring the question. Because this is a one variable system, I'm going to use the very first Taylor expansion equation that we use in the class. So the function's value at that operating point plus function's derivative with respect to your variable when x is equal to your nominal value minus x bar. Because you're trying to linearize around to your operating point, x bar will be equal to 2. So, and your function, let's just write this, f of x is equal to 0.2 x cubed, and this is a nonlinear function because of x cubed. Function's value when x is equal to 2 will be 0.2 times 8, which is 1.6. And function's derivative with respect to x when x is equal to 2 should be, guys, we multiply the coefficient with the power, and then we will reduce the power. So it will be 0.2 x squared when x is equal to 2. So you have 0.2 times 4, which is 0.8. From here, your linearized equation, which is just a function of x, will be equal to 1.6 plus 0.8 times x minus x bar, which is 2. So from here, your linearized equation will be equal to 0.x plus 1.6 minus 1.6, which is just equal to 0.8x. Let me confirm this. Let me go back. No, actually, I made a mistake. Let me correct my mistake. So somewhere else, as you see in the equation, there is this mistake. So here is your f of f bar, and then once you take the derivative, it's not 0.2 x squared. It's actually, so there's a big mistake that I did. So that's why it's really good to compare your results with Matlab just in case you miss it. So I have actually, when you take the derivative, it should be 0.6 x squared. So I have 0.6 times 4, which is 2.4. Then the linearized equation, it will be, guys, 1.6 plus 2.4 times x minus 2. The linearized equation, one more time, will be 2.4x plus 1.6 minus 4.8, or it's just equal to 2.4x minus 3.2. And this is a linear equation. So this is going to be the equation. And sorry for the mistake. Next, let's actually now solve for the last example here, which is also a two-variable equation. We will be trying to linearize the equation for a given range, but don't forget, if you're given a range, please just take the midpoints. So here is my equation. So you have z, which is a function of x and y, is given by x squared plus 8xy plus 3 times y squared. And the nominal values of x, which will be the midpoint here, is 3, and y bar will be equal to 11. Now remember, Taylor's expansion for two-variable system will be function's value at those two given points plus continue with the partial derivatives now, multiply them with their difference, so plus df dy when x is equal to x bar, y is equal to y bar multiplied by y minus y bar. Again, I really recommend you to just separately calculate those three terms. I have f of 311. So this gives you 9 plus 8 times 3 times 11 plus 3 times y squared is 11 squared. So from here, because I don't have a calculator with me at the moment, I'm going to go to Matlab and ask for help. Again, let's just start with a new one. So my two variables are sims x and y. My original equation is x squared plus 8 times x times y plus 3 times y squared. Let me confirm. I have x squared plus 8xy plus 3y squared. You can actually go ahead and print your answer here just to make sure you didn't make a mistake in the beginning, so everything will be correct after. Remember what we did? I'm trying to find the nominal value. So let's substitute in f wherever we see x and y. So I'm trying to copy and paste this. Okay, let me just bring this comment here because I'll be using this often. Instead of just typing it over and over, my values for x and y are 3 and 11. Okay, let's calculate this. Nominal value is 636. Let's continue. Now function's derivative with respect to x when x is equal to 3 and y is equal to 11. Remember what we said? If you're trying to differentiate with respect to x, anything next to x like 8 and like 8 here along with y will be considered as coefficients. So take the derivative of x squared with respect to x, this gives you 2x. Taking the derivative of 8xy with respect to x should be equal to 8y. And now I'm trying to take the derivative of 3y squared with respect to x. There is no x, so it should be 0. But remember, we will plug in 3 and 11 for x and y. So I have 6 plus 88, which gives you 94. Let's go back and do exactly the same thing. Now remember, I'm trying to take the derivative first with respect to x, the original function with respect to x. I don't need to print this anymore. So the derivative is 2x plus 8y. And now let's continue with the substitution. So I will say fx nominal is equal to, in fx, and here are my values, not 6 and 11, but 3 and 11. Go ahead and confirm your solution, which looks correct. Now we are going to take the derivative with respect to y when x is equal to 3 and y is equal to 11. So remember your equation, it was x squared plus 8xy. So I have first 8x plus 6 times of y when x is equal to 3 and y is equal to 11, which gives you 24 plus 66, which gives you 90. Let's do exactly the same thing. I can actually copy these two. Oops, sorry. There you go. Let's rename them as fy, but take the derivative with respect to y. Then I have fy instead of fx, and this should be fyn. And print the solution, it's 90. We didn't make any mistake again. That's a good thing. Now the linearized equation, it should be equal to function's value plus partial derivative with respect to x multiplied by x minus x bar, partial derivative of f with respect to y multiplied by y minus y bar. So then after this, you have to go ahead and simplify your equation. So this gives you 94x plus 90y, and I don't know the calculations here, so I will refer to my best friend. Matlab f linear should be equal to the nominal values plus f of x nominal multiplied by x minus 3 plus fyn multiplied by y minus 11. So Matlab will just simplify this equation. 94x plus 90y minus 636. So we solved the problem. Let me go back, and if it's asking for any error. So our range was from 2 to 4 and 10 to 12. So let's just even if it was not part of the question. So let's say I will give you two different points. Let's say x is 0 and y is 5. So how much error are we making by using the linearized function instead of the original function for x is 0 and y is equal to 5? And I will go back to Matlab. I will bring this whole part. Let's copy this. go back here. I will have a section break and Control V. Now in f, x and y, we are going to use our new values 0 and 5. And in the linearized equation, let's use exactly the same numbers, 0 and 5. And here is the percent error. And I'm using the same function names. So the error will be 348%. It's really big error. So it's probably not really acceptable to use the linearized function for those two new points, 0 and 5. Thank you very much for your time.